question involves correctly sizing the secondary conductors for a 225 kV transformer with a 480 volts delta primary, 270 amps primary side current, and a 208 Y/120 volt secondary with 625 amps secondary current powering three 208/120 volts, 200 amps panels. The specific code reference is National Electrical Code Section 240.21c6, which deals with the protection of transformer secondary conductors. The confusion arises from the interpretation of the voltage ratio in the context of this code section. National Electrical Code Section 240.21c6 states that the secondary conductor shall have an ampacity that is not less than the value of the primary to secondary voltage ratio multiplied by 1/3 of the rating of the overcurrent protective device, or OCT, protecting the primary of the transformer. To clarify the calculation, firstly determine the correct voltage ratio. The voltage ratio is calculated by dividing the primary voltage by the secondary voltage. In this case, it is 480 volts divided by 208 volts, which equals approximately 2.31. Secondly, identify the primary OCT rating. It is given as 270 amps. Thirdly, apply the formula from National Electrical Code Section 240.21c6. Ampacity of secondary conductors equals voltage ratio multiplied by 1/3 of the primary OCT rating. This translates to 2.31 multiplied by 1/3 of 270 amps. 1/3 of 270 amps is 90 amps. Then 2.31 multiplied by 90 amps equals 207.9 amps. Therefore, the secondary conductors must have an ampacity of at least 207.9 amps. To select the appropriate wire size, consult National Electrical Code Table 310.16, which provides ampacities for different wire sizes and insulation types. For conductors rated 75 degrees Celsius, which is a common insulation temperature rating, a copper conductor with an ampacity of at least 207.9 amps would require a minimum of number 2/0 American wire gauge, or AUG, copper conductor. For aluminum conductors, a larger size would be needed due to aluminum's lower conductivity. A number 4/0 American wire gauge, or AUG, aluminum conductor would be appropriate. The initial calculation attempt was incorrect because it seems to have used an incorrect secondary voltage of 110 volts instead of the correct 208 volts and misinterpreted how to apply the 1/3 factor in the formula. Using a number 10 wire, which has a much lower ampacity, for 625 amps potential secondary would be extremely dangerous. Such a small wire would quickly overheat, leading to insulation damage, melting, and potentially a fire hazard. It is crucial to ensure that the conductors are adequately sized to handle the potential current. The potential consequences of undersized conductors include overheating, insulation failure, electrical fires, and equipment damage. Always consult the National Electrical Code and local electrical codes to ensure compliance and safety. Always double-check calculations and consult with a qualified electrician if there are any uncertainties. In summary, the correct calculation involves determining the voltage ratio, which is 480 volts divided by 208 volts equals 2.31, and then applying the formula from National Electrical Code Section 240.21c6. The secondary conductors must have an ampacity of at least 207.9 amps, requiring a minimum of number 2/0 American wire gauge, or AUG, copper conductor, or number 4/0 American wire gauge, or AUG, aluminum conductor. This ensures a safe and code-compliant installation. The misunderstanding likely stemmed from an incorrect secondary voltage value and misapplication of the formula in National Electrical Code Section 240.21c6. Always verify voltage values and carefully follow the code requirements to prevent dangerous situations.